Welcome back. Section 4, Chapter 14, last section, gases, mixtures, and movements. And we know that gases are always in motion because they never get to absolute zero, and they mix with each other and move around. Some of you might end up climbing Mount Everest someday, and you probably know that it's pretty darn tall and the atmosphere is pretty thin, and there's not enough oxygen for people, most people anyway, to survive even after you get acclimated at base camp for a while. And so we're going to find out about that. So John Dalton, remember him way back when, the English school teacher in Manchester, England. He worked out some ideas about gases and how they mixed, which led him to the concept, the idea that matter was made of little particles, which we call atoms. So he has a law called Dalton's law of partial pressures. Each of the gases that compose our atmosphere, nitrogen being the bulk of it, then some oxygen, a little tiny bit of carbon dioxide, argon gas, which is a noble gas, and other gases mixing together, each of them has a certain partial pressure. They contribute to the whole. Okay? Each gas adds a little more pressure to the atmosphere until we get 1 atmosphere of pressure, 101.325. So very simply, Dalton's law of partial pressure looks like this. The pressure total is equal to the pressure from gas 1 plus the pressure from gas 2 plus the pressure from gas 3 on out to however many gases. Usually they put a plus P to the N on here, so N being some variable number, not moles. And then this is another image from your textbook. In container A, we've got a pressure of 100. Container B, a different gas has a pressure of 250. Container C, a different gas of 200. Put them all together at the same temperature, and they will give you a pressure for the total of 550, 100, 250, 200 equals 550. Each one contributes a little bit more. Turns out that those pressures, again, if the volume's constant, if the temperature's constant, that's a really key thing to keep in mind. Also, we have to keep in mind that there's more than one variable that affects gases. Okay? If you're going to be able to stay alive, you have to have a pressure of oxygen at least 10.67. Higher than that would be better, to be able to stay alive. So most climbers need some compressed oxygen when they climb up there. Professor Dave again, I'll have you watch him. Graham's law is often called Graham's law of diffusion, but it's really technically effusion. I'll tell you the difference here in just a minute. You might remember osmosis from biology, how higher concentration moves to lower concentration across a membrane. In diffusion, it's similar. Higher concentration, this is bromine gas vapor, moves to lower concentration without a membrane, without a barrier. And then eventually, okay, it will fill the entire container. And of course, honestly, eventually, it will leave the container if we wait long enough. Effusion, on the other hand, is moving through a tiny opening, okay, a little hole in a barrier. Those bouncing around gas molecules get through that hole and can get out. And it turns out, what Graham figured out is gases with lower molar mass are going to diffuse and effuse faster than gases of higher molar mass. And of course, that's assuming that the temperature is constant, doesn't change. They have the same temperature. So the lower molar mass gas has the same temperature as the higher molar mass gas. That's hard to say. All right, so rate of diffusion is inversely proportional, and here's where it gets weird, to the square root of the gas's molar mass. So the bigger it is, the slower it goes. So if you push on a VW, you can get it moving. if you, I had to bring that one back, if you push on a bus with the same amount of force, it's not going to move as fast. Okay, so um, little things for the same force, the same temperature, same kinetic energy are going to move faster than big things. Okay? A helium-filled balloon is going to deflate sooner than an air-filled balloon. How come? Well, you know that helium is smaller than nitrogen and oxygen, I hope. They're less massive, and so it's going to move through an opening faster. Excuse me. The rate of effusion of A is inversely proportional to its mass, so it has to go on the bottom. Rate of diffusion of B inversely proportional to its mass. So since B is on the bottom, molar mass goes on top, and it's the square root of those two things. I'm not going to make you do any calculations with that this year. You're welcome. But here's how they calculate it out. So helium is going to effuse or diffuse almost 3 times faster, okay? More than 2.5 times faster. This is a classic demonstration. It's a pretty short video. Hydrochloric acid and ammonia, when they contact each other, make ammonium chloride, which is a white solid. And this can be used to measure, and this is a glass tube. Put a sample on either end. One end has ammonia, oopsie, and one end has hydrochloric acid, and you can actually measure the distance. I've done that as a demonstration previously. Not for you guys, but in previous years, sorry. So this is Hank being silly again, if you want to talk about stinky, rotten eggs. I'm going to make you watch this right now. These are 2 identical balloons, and here we go. Slightly different number than what the book had. So that was pretty quick and painless, I hope. So smaller particles move faster than bigger particles if they're at the same temperature. This is another video a little bit about Graham that is in the chapter thing, but I don't think I'm going to have you actually, you don't need to watch that. So ends chapter 14 on gases. We'll have a little bit of work on gas law calculations. And that's it. Hope you're well. Bye.